Hello everyone and welcome to the 18th topic of Introduction to Remote Sensing course, and in this topic we are going to discuss a very upcoming part of remote sensing, branch of remote sensing, which is called hyperspectral remote sensing. As you know that so far we have been discussing the passive remote sensing, also we have discussed the active remote sensing, but this is, though it is a passive remote sensing, but it is hyperspectral, has got many applications which are very specific, and it is going to be very popular technique for certain types of applications of remote sensing. So what basically hyperspectral remote sensing, earlier we used to have spectrometers and used to take in the field to create the spectral curves of different objects, different rocks, different minerals which are present on the surface of the earth. But now it is possible to even create these spectral curves using hyperspectral remote sensing as well, plus finding out other mineral resources, alteration zones, changes in vegetation, stresses conditions, different stress conditions in the vegetation, and so on and so forth. So this is becoming very popular, very important branch of remote sensing which is upcoming. So hyperspectral term we use when we are having too many or excessive bands. So we like initially, like we had when Landsat MSS, we had only 4 bands. Now in Landsat OLI series we are having 11 bands. So we have progressed only that much, but now it is possible to have hundreds of bands. We will see some examples of currently operational satellites or in hyperspectral region which are having more than 200 channels. So maybe in future we, instead of having hyperspectral remote sensing, we might be even thinking of ultraspectral remote sensing of hundreds of bands within one sensor. But one thing one has to remember, more the number of bands are there, more the data has to be handled, and this is really huge data sets which is being generated nowadays under this hyperspectral. So this, because this is also a passive remote sensing, so it's a reflected or emitted radiation, whatever during daytime, solar radiation or emitted radiation, which can be measured at a very fine spectral resolution. So it's a continuous, that means there are no gaps. Like if I take example of Landsat ETM plus sensor, or in OLI series Landsat 8, that there are gaps between one band and another band because of atmospheric windows and other reasons were there, or absorptions. But now in hyperspectral there is no gap. One band ends, another starts. So it's a continuous data which is being collected. So very fine spectral resolution, that means maybe in a nano meters or in 0.1 micrometer or something like that, and to identify different materials which are present on the surface of the earth, and so we should be also able to create, if it is flying or if image is of belonging to a known area where we know that what kind of materials are present, then we can make spectral curves as well for other purposes in other fields of remote sensing. So basically 2 purposes: to identify different materials which are present on the earth, create a spectral library for future use. Hyperspectral remote sensing basically detector records hundreds of spectral bands of relatively very narrow bandwidth, maybe 5 to 10 nano simultaneously. On this, all this data is being collected, huge data. With such detail, the ability to detect and identify unique trends in land and atmospheric data sets is greatly improved, so that each and every variations within each and every object which are present on the earth can be recorded very accurately, including part of atmosphere. Because more focus is going on nowadays on the atmosphere as well, because of global changing and other things. And it also, hyperspectral remote sensing also allows to have a specific analysis for a particular type of land cover. and emissivity levels of each band can be combined to form a spectral reflectance curve. This is what I said, that another purpose of this, that spectral reflectance curves can also be created. Earlier the curves which we will see very soon, or we have also seen some like curve for vegetation, curve for water body, bare soil, rocks and other things, were taken at only at certain points, and then rest of the things were connected. But here in hyperspectral remote sensing, for each nanometer you are having one value, and therefore you are having a continuous curve and not a interpolated one. So that is the another advantage of hyperspectral. If we compare simple multispectral, then you are having gaps between one band and another. But in hyperspectral, all bands are continuous. So here, this was, if we say these were the discrete bands, not continuous bands, and here you are having continuous bands. So therefore, if I have to make a curve, then all top and in between the interpolation was required basically. But here now for each wavelength I am having one value of reflectance, and therefore a continuous curve, reflection curve or emission curve can be generated. Same way here, that broadband, we used to have very broadband, still we carry broadband in visible part in panchromatic sensors are there, even on Landsat 8. There is a relatively quite broadband in visible and short wave infrared, long wave infrared, all these were very broadband. When we came for the multispectral, then these bands, this visible part has been divided in three parts. Short wave was also divided in three parts. Later on in the hyperspectral, you are having continuous, and hundreds of such bands are there. And of course, if we go for ultraspectral, maybe in future, then we will have thousands of bands. And you can think that the handling of data would be really exponential in terms of their processing. But anyway, the processing tools, computer, hardware, software, everything is developing. So it would be possible even today like to handle hundreds of bands data, in future maybe thousands of bands data, and we will have very accurate spectral curves and the analysis of different materials which are present on the surface of the earth. Like in multispectral, we used to have just point data against a certain wavelength, but here in a continuous. So minimum identification was possible in multispectral, and low confidence we had. Here in case of hyperspectral, it's a maximum identification, everything could be identified. A slight change in the spectral curve can be correlated in different parts of EM spectrum. High confidence is there, and here the field knowledge and lab analysis was required. But here in future, we will have these standard curves for different materials, like here for different minerals, kaolinite, gypsum, alunite, dolomite, calcite, chloride, all these are having different spectral curves. So these can be used to classify hyperspectral images very easily without having any prior field knowledge. So that can be also possible in future as well. Now we continue on this multispectral versus hyperspectral. As we know that there are separated spectral bands, there were gaps between one band to another, whereas in case of hyperspectral does not have any spectral gaps, say continuous data. Here is the discrete bands, here continuous bands. Wider bandwidth we had initially like between 0.4 to 0.5. So this was now considered as a wider bandwidth, whereas here you are having in nanometer narrow bandwidth data is there. So very high spectral resolution. Coarse representation of spectral signatures, a complete representation of spectral. It was a discontinuous spectral curves. Here is a continuous spectral curve, unable to discern small differences between reflectance spectra. But here it is capable to detect subtle spectral features. Smaller data volumes, not much in today's terms, it was not much data, but at that time of course it was huge data, because now computers and our storage capacity has increased manifold. So today's reference, it looks a smaller data sets, but nowadays even as per today's standards, hyperspectral data is a larger data volumes. So they, in that way it's a minus point, but it is providing a completely continuous data set, and fewer problems with calibration. Calibration problems were very limited, but now we have to, because we are having data of very narrow bandwidth of 10 nanometer, and therefore radiometric and spectral calibrations are very much required, and these are very time consuming processes. As can be seen here is that suppose this is one this false color composite, but in 3D, when we are having hundreds of bands, then like here Z equal to spectral bands, then as can be seen for in the sides, you will have these not really slices but continuous depth of information, reflection or emission information about an area. Earlier we used to have just one color composite, now we can have a complete cube of information. So it has definitely added one more dimension to standard remote sensing. This how this spectrometer is there, as you can realize that there are some sensors which we will be discussing soon, having 224 spectral images taken simultaneously. So we can detect each objects and their corresponding responses in throughout these 224 spectral images. Like here, immediately it becomes very easy to make a spectral curve if I am having some prior information that this area is 100% having vegetation cover. So then I can say that this is the spectral curve. Automatically also, when the pixel by pixel data is collected or images are generated, then using these standard curves, after that, once the standard curves are generated, then classification can be done very easily. So likewise, water, soil and everything, these things can be done. As you see that the vegetation, water and soils curves are very easy to interpret. We know that where there is a higher reflection, where is a less reflection or absorptions, but in case of atmosphere it is a complex thing. So anyway, that has to be also looked into, and hyperspectral remote sensing also providing that kind of information as well. So spectra of two materials with very different reflection and absorption properties, when sensed with a wide band in a normal remote sensing like Landsat MSS or TM or IRS list 3, list 4, may have the same response and cannot be discriminated. But in case of when we are having continuous spectra, we will find at place between these two objects in their respective spectral curves where these can be differentiated. So this is what is meaning here, that whereas the continuous spectra, if I am having, each spectral element is analyzed using hyperspectral sensor or imaging ray spectrometer. So that is the biggest advantage of having hyperspectral. Hyperspectral image analysis techniques can drive using the field spectroscopy, which relate to a molecular composition of a particular material with respect to corresponding absorption reflection pattern of light at individual wavelength. Because the advantage here, you are having continuous spectra, not a discrete one, and therefore it is easy to detect the slightest changes in two objects very easily. Spectral information of known material can be collected in laboratory settings, and then these spectral libraries can be used further, as mentioned also earlier, that different methods can be employed to compare the reference spectra with obtained spectral curves. And these another approach is in spectra that we create a ratioing which dividing every reflection value to a difference spectrum by respective value of image. So once that data is collected, then further processing is also possible. This Everest was one of the sensors which was designed about 20 years or more, and it was a airborne sensor, Hyperion, which was covering visible and infrared part of electromagnetic spectrum, but it was continuous. It was a hyperspectral category. It had 224 bands, huge number of bands. Just compare Landsat 8 data, just 11 bands, 224 bands, and 0.4 to 2.5 micrometer. So it's covering almost the same wave EM spectrum as in Landsat 8, and except that thermal flies on this ER2 or low altitude twin otter. So this was since it was a airborne, so that data wherever they felt, they flown the aircraft and collected the data. And of course it developed the concept and everything, and later on once it was realized that now the similar kind of sensors can be sent on a satellite, so it becomes a spaceborne rather than airborne, and then you will have continuously data for all parts of the globe. And this is what it is done by putting a Hyperion sensor on board of a Earth observing satellite 1 of NASA, and this had almost the same kind of bands and other things which we will see. This was the main purpose is to demonstrate the technology. So this was a technology demonstration mission, includes Hyperion instruments, and it has 220 bands, because everything for a decade, everything were tested on average, which was airborne, and almost same number of things were there, and of course then a number of bands were little bit reduced, 220 bands. This EM, the bandwidth or the total bandwidth coverage was remained same, because in the experiment was found it is all right. And then swath of course is little different. It's a tiny strip of just 7.5 kilometer and the length wise 100 kilometers. So one scene is covering a very tiny strip, and the reason is of course the huge data it has to scan in 220 bands, and same time it has to send towards the earth or record on board. And however, for many development and validation studies, still handheld sensors are used. So you go in the field spectrometers and collect the data, but this is a very good development has taken place. The data is available for some parts of the earth. Now on further we will see Hyperion imaging spectrometer on board of NASA EO-1 satellite, which was a demonstration purpose mainly. It is a push broom sensor of having the altitude of 7.5 kilometer. The swath width is 7.6 kilometer, which is a relatively very narrow, and it has a 98-degree inclination, flying in formation of with reference to Landsat 7, just 1 minute apart, so that it can be also checked along with the Landsat 7. Spectral range was as mentioned earlier 0.4 to 2.5 or 2.4, and each band had the 10 nanometer bandwidth. There were 220 spectral bands. Spatial resolution is not as that high as one would like to have, because now we are talking about 30 centimeter, but still 30 meter spatial resolution is quite good. It is comparable with the Landsat latest series, so that for those corresponding bands where Landsat is also having can be compared here as well. So with this this radiometric resolution is also very high, a 12-bit data. So huge data of 220 bands at 12-bit is being generated for all parts of the globe. Now when we look the applications, some of the applications I have already discussed. The applications, the major one which are coming, so let's start from top, the mineral map. Doing the mineral mapping, doing searching for alteration zones. Slight change in mineral properties can now it is possible to detect by using hyperspectral remote sensing. Of course it has to be exposed. If it is covered with vegetation or soil, then it's a different thing. Even in the soil properties, slight change in soil properties can also be discriminated. So hyperspectral remote sensing can play major role in mineral mapping, mine tailings monitoring. This is again because mines create lot of output, and those things can also be monitored. Now soil fractions, soil mapping, overall soil mapping, very accurate mapping, and other things can also be done. Canopy liquid water, whether there's plants are having stress due to the water or not, or trees or agriculture fields are having the same thing, can also be assessed here. Leaf area index can also be measured using hyperspectral remote sensing, which will help in agriculture. It will tell that whether the crop is under water stress or not. Those things can be assessed very easily. Chlorophyll concentration, again related with the health of the vegetation, whether high chlorophyll concentration is there or less, which part is having less, which more. All these things can be measured or sensed by the hyperspectral remote sensing. The crown closure of plants, kaolinite, which is again soil mapping, and the water vapor. Water vapor or the atmospheric thing can also be used in that application, the hyperspectral remote sensing. So, lot of applications are there: mineral and oil exploration, overall in agriculture, environment, water vapor and other things, surveillance also, in chemical imaging, especially for water bodies where some effluent or pollutant water is coming. So, in where because you are having a continuous spectra, so you can really detect individual probably individual elements or concentration of different pollutants can also be measured with this one. Of course, the spatial resolution is 30 meter, but doesn't matter. Still, in lake water or in sea water, such concentrations of chemicals or sediments can be measured very easily. Further applications overall in atmosphere, water vapor, cloud properties, aerosols because of increasing pollution, aerosols has become very important to study. So, in hyperspectral remote sensing it is possible. Ecology, chlorophyll, leaf area, cellulose, pigment and lignin, in earth sciences, in geology, mineral and soil types, rock types, lithology can be discriminated. In coastal waters, as I have said, chlorophyll, phytoplankton, dissolved organic materials, suspended sediments, all these are important to map. And then snow and ice also, that what is the snow cover fraction within, whether it's a complete ice or complete snow or some part of snow, and so thing, grain size and melting and other things, and biomass burning. This is becoming a big issue, that we can have even a subpixel temperature or a smoke detection and other things. Because of whether that smoke is coming because of biomass or smoke is coming from coal burning, that too can be detected, because both smoke might have a different spectral curves, which can be only detected through hyperspectral remote sensing. So, likewise it is adding to many applications. Mineral exploration I have already covered, agriculture, forest production and so on. There are some specific geologic applications. Mineral exploration is the basic application area of hyperspectral remote sensing, and the purpose here is to distinguish spectral features of different minerals, and so that in short wave infrared region, so that the different mineral or bearings of different thing, whether they are having water or other things, they can be detected very easily. And likewise an area can be classified based on, this is the example of average data application. So, different types of iron bearing minerals were classified like chloride, goethite, hematite, jazzite, jarosite and pyroxene, and of course some places where no detection, but it has become only possible because of hyperspectral data. But one thing, as I have already mentioned, is too much data to handle. Even with today's systems, image processing softwares available with the standard installations, it is not that easy to handle. But anyway, in future this has got future, this will develop few more applications areas. So, wide variety of minerals can be detected, they can be mapped, and people have done different kind of works to detect soil properties, to detect vegetation species, to map extent of different plant species, to study plant canopies chemistry, and to detect vegetation stress. That is very important application, especially in agriculture, whether a crop is suffering from water stress or crop is suffering from certain types of disease or other things, or a deficiency of certain minerals, fertilizers, that can be detected. And of course it has got some military applications, and to map areas contaminated by mine drilling or other pollutants and so on. So watercolor to determine which microorganisms are present and locate the pollution source. So wide applications are there for hyperspectral remote sensing. People have already done some work using average data on this. And similarly, like for mineral exploration, which I have already covered, that different spectral curves for pyrophilites, calcite, muscovite gypsum can be detected very easily, because you are having continuous curves. Same with different types of clays, kaolinite, montmorillonite, alunite, all these can also be detected. In vegetation, basically if a plant is suffering from some stress because of water or some other reason, the spectral curve will shift towards the left, means towards that red edge, and that can be detected in hyperspectral remote sensing. And then sharp reflection changes occur in spectral region between this and this, since we are having bands at almost every 10 nanometer, so these things can be detected very easily. And this red edge of shift in red edge towards red edge can be detected in case of vegetation, in case of crops and other things. So crop identification, and which can be done solely on the spectral curves which will be developed in future. So standard spectral curve is compared automatically by the computer based on the new input image, and classification can be done, and then you know that whether what kind of crop it is, whether it is having healthy conditions or not, those things can be detected very easily. Same in the mineral detection and mapping can be done. So it has got really wide applications, and future applications will also come. So far only one sensor on board, a satellite is there, but very soon hopefully we will have more data handling capabilities, more types of analytical tools would be available, and this will serve a lot of purpose. So this is just an example of like in true color image, this is what you see. This much only discrimination is possible, but in hyperspectral remote sensing this kind of detection is possible. So this brings basically to this water quality also. It can be done, as I was mentioning, in the river water or lake water, this thing can be done. So this brings to the end of this presentation. Thank you very much.